Your CPU can execute billions of instructions per second. So why does your code still feel slow? Why does one NumPy operation fly while another doing the same math suddenly collapses? Why does a transpose or a slice sometimes destroy performance even though the data hasn't changed? The answer is not Python and it's not NumPy tricks. The answer is the CPU itself. In this video, we are going inside the processor. We'll see how data actually reaches the CPU, why memory layout matters more than algorithms, and how NumPy is deliberately designed to fit caches and vectors units exactly what they want. Once you see this, you have better understanding of this performance optimization. Let us start with the reality that most programmers underestimate. Modern CPUs are rarely limited by computation. They are, however, limited by data movement. Adding two numbers is cheap. Multiplying numbers is also cheap. Even complex floating point operations are cheap. What is expensive is getting the data from memory to CPU at the right time. This gap between computation speeds and memory speed is so large that CPUs have been redesigned around it. That is why caches exist. Instead of reading directly from the main memory, CPUs use several layers of cache. If you want to know about the CPU cache, you can of course watch this video. We'll not go through the CPU architecture in this video, of course. But to have a better understanding, these caches are small. They're extremely fast and very close to the CPU core. When CPU needs a value, it doesn't load just that value. It loads the entire cache line, usually 64 bytes at once. That cache line contains the requested value plus nearby values. This design only works if memory access is predictable. If your program reads memory sequentially, the CPU can guess what you will need in the next and fetch it ahead of the time. Execution stays smooth. Pipelines stay full. The CPU stays busy. If your program jumps around the memory, the CPU cannot predict anything. It stalls, waiting for the data while billions of transistors sit idle. This is where NumPy's design becomes critical. A Python list stores references to objects scattered across the memory. When you loop over a list of numbers, the CPU follows pointers to random locations. Each access risks a cache miss. A NumPy array stores raw values in one contiguous block. When NumPy processes it, the CPU sees a clean linear memory stream. That single difference is often the difference between saturating the CPU and starving it. This leads to a common misconception. Clock speed matters far less than whether the CPU can keep its execution unit busy. Now let's make this concrete with NumPy. The array is contiguous. Each element sits right next to the previous one in the memory. When NumPy loops over it, the CPU streams through memory in order. Cache lines are fully utilized. Now look at a strided view. The data has not moved. The values haven't changed, but the access pattern is completely different. Each step skips over the memory. Cache lines are partially used. Prefetching becomes less effective, and CPUs spends much more time just waiting. Nothing about the math changed, only the way memory is accessed. This explains why some NumPy operations slow down dramatically after slicing, transposing, or reshaping in certain ways. NumPy didn't suddenly become inefficient, the CPU did. This is also why NumPy sometimes chooses to make a copy of an array. A copy data can feel wasteful, but if it restores contiguous layout, the overall computation can become much faster. You need to remember that the CPU rewards locality. NumPy is built to preserve it whenever it's possible, but caches are only one part of the story. Modern CPUs do not just process one number at a time. They process many numbers in parallel using vector units. This is called SIMD, single instruction multiple data. A single instruction can add 4, 8, or even 16 numbers at once, depending on the hardware, of course, and depending which year you are watching this video. For this to work, data must be laid out uniformly in memory. Elements must be the same size. The strides must be predictable. The alignment must be correct. NumPy arrays satisfies these conditions by design. When NumPy executes a loop in compile code over a contiguous array, the compiler can automatically generate vector instructions. One instruction operates on many elements simultaneously. This is exactly where massive speedups come from. Python loops cannot take advantage of this. this. Python integers are objects. Their size varies. Their layout is unpredictable. The CPU cannot pack them into vector registers. This leads to another myth. Being written in C is not enough. What matters is that NumPy constrains data and execution so that the compiler and CPU can do their job. This also explains why some changes in code can have outsized performance effects. A transpose may turn contiguous access into a strided access. A reshape may preserve layout or even break it. A copy may slow things down or makes everything fast. From the outside, these effects look unpredictable. From the CPU's perspective, however, they are completely logical. The CPU wants three things: predictable memory access, large chunks of works, uniform data. NumPy is designed to provide exactly that. NumPy arrays are contiguous blocks of memory. Strides allow NumPy to reinterpret memory without copying. Bulk operations move loops into compile codes. Caches reward sequential access pattern, and vector units reward uniform aligned data. Each layer reinforces the next. This is why NumPy feels low level compared to Python. It doesn't try to hide the machine. It aligns with it. Once you see NumPy through this lens, performance stops feeling like a collection of tricks. It becomes a consequence of design decisions that respect hardware reality. This leads us to the final results. NumPy is not just a library for numerical computation. It is a hardware-aware execution model embedded inside Python. It translates high-level array expressions into memory access patterns and instructions that modern CPUs are optimized to execute. That's why NumPy is fast, and that is why its behavior sometimes feels strict or unforgiving. And that's why understanding memory and hardware matters more than memorizing APIs. If you understand these three ideas, you understand NumPy. And more importantly, you start seeing performance not as something mysterious or magical, but as something mechanical. If you have ever experienced such performance difference when you are using NumPy in your program, please share it with others in the comment down below. If you enjoyed this topic, don't forget to like the video and subscribe to the channel to not miss the next ones. Until the next video, good morning, good afternoon, and good evening. Bye.